Good morning, guys, and welcome back to the channel. It is currently a Saturday morning as I struggle to get this video out in time due to being out of town the last weekend, but at the same time, I'm still procrastinating hitting legs. So hopefully this one will take a decent amount of time so I don't have to go ahead and squat because I hate that. Anyways, today we're going to be talking about Dropbox and Google Drive, so we can go ahead and get into that and do video number 3. Okay, so as I mentioned, today we're going to be talking about Dropbox or Google Drive. The one thing I should note is that as I actually think about the design that I went for this video, it turned out to actually be pretty simple to what we did in our last kind of social media, Twitter, newsfeed post video. So if you haven't seen that one, I would recommend watching that first. I wouldn't say I'm brushing through things, but there are things that I went a little bit more in depth into last episode, and as a result of that, I think it is going to benefit you to actually be watching those in order. Anyways, let's talk about what Dropbox and Google Drive actually are. So for those of you who are uncultured, we've got this idea of like some sort of cloud file system, which is just a black box. And if we've got me over here writing a file to it, that file might be shared with, 3 different users, 1, 2, and 3. And then as you can see, they might be on their phone over here. That change is going to be instantly propagated to them. So this would be user 1, user 2, user 3. And of course, assuming they have write permissions, they can do the same thing, write back into this, and then that should be propagated back over to me, barring any sort of write conflicts or anything like that, and we'll talk about that in a bit. So let's actually go ahead and formalize the requirements of this problem. So for one, like I mentioned, if you're a user, you can create and upload a file to our Dropbox or our Google Drive. Another thing is that multiple different users can see those files, as we showed in the above diagram. Another thing is that changes to files should be propagated to all the devices with access. I shouldn't have to load up a client and then be like, hey, can you give me the most updated file? I should be able to actually just see it, assuming that client has been passively open in the background. So it should be propagated. And then, of course, this is a small requirement, but just nice for history's sake. We should be able to see versions of files. So after a file is edited, we should be able to recreate the older version of the file, assuming that there is an older version. And so again, for a problem like this, you can see that it's not necessarily the reads or the writes that are going to be bottlenecking us. There's probably not that much of either of them. It can just get a little bit complex to do all of this versioning, the sharing with the users. And so I think we're going to be less bottlenecked by speed and more bottlenecked by actually, keeping the program to be not too intensive on our client devices. So we can think about how we'll do that in a little bit. Okay, so let's come up with some quick capacity estimates. So as per usual, I'm pretty much just making these up. They're very hand wavy, so don't come after me too hard. But I'm assuming around 1 billion users, around 100 docs per user, which I think is pretty reasonable. Obviously, there are going to be some users who have in the thousands or even more than that, but I think 100 is pretty reasonable for the most part. Assuming each document is around 100 kilobytes, so that's saying around 100,000 characters per document, I also think that's reasonable. Some might be in megabytes, not really a huge deal. Then if we're going to go ahead and see how much storage that accounts for in terms of actual documents themselves, we've got 1 billion users, 100 documents per user, 100 kilobytes overall, and that comes out to 100 terabytes of docs, which is really not too much. I'm sure that in reality, companies like Google Drive and Dropbox are storing quite a bit more than that. I mean, I personally have almost 12 gigabytes of storage in my Google Drive, so it's clear that there are going to be certain power users taking up quite a bit more than that, but assuming we use something like an object store like S3, effectively that's infinitely scalable. Storage is not going to be our constraint here. Okay, so another thing is that most documents are shared with less than 10 people, and some might be shared with many thousands. And this is going to come in handy, or rather it's going to be important when we discuss how we can actually propagate the changes for a given document over to all of the interested users. So I wrote that over there. Okay, moving on from capacity estimates, let's start talking about document permissions. So as I mentioned, a given document can be shared with multiple different users. And when I say document, I use that term interchangeably with file. That being said, though, we can store any type of arbitrary file. It doesn't just have to be a document. So I'm sorry if that gets confusing at times. That's honestly an error on my part, but hopefully it still makes sense. So the schema for something like this, as I go over here, would be we've got a user ID on one side, a document ID on the other side. So if a user ID and a document ID appear together, that means the user has access to that document. Now, to keep this quick, to keep basically the queries quick on this table, I feel that it is a good idea to index based on the user ID and also shard our partitions based on the user ID. The reason being that we are occasionally going to have to query and figure out for a given user which documents do they have access to. This might happen if you didn't have a client open, then you start it up after a long while. We need to figure out quickly which documents I might have access to so that I can actually pull them from the server. It's not always going to be the case that we get to push the documents to the user. If their client's not literally open, then there's just nothing you can do about that. So to give some perspective on what that might look like, that would literally just be like, if I'm user 1 and user 1 lives on shard 1, then I would first query that, and then I would go and query this black box of a file service to get all of our files. So hopefully that makes a little bit of sense behind the indexing and the sharding choices, but this table schema should be simple enough. So then a quick tangent before we go onwards is, what actual type of permissions database should we be using? Now, in order to decide a database, typically I like to think about what type of replication is feasible for us. And of course, if we do need a type of replication that's going to enable better performance, whether, we have performance constraints here to actually justify that. So I was thinking in this case that single leader replication may actually be best. So the reason for my thinking there is that imagine that we were to give a user permission for a certain document, and then we were to quickly remove permission for that user. So if we had like a leader 1 on the left over here and a leader 2 on the right, keep in mind that adding a user and giving them permission and then removing it is a causal dependency. It doesn't make sense to remove a user's permission unless they've already been added. And it wouldn't be great as well if for some reason that remove didn't go through, right? So when these guys eventually sync up with one another, you can see that the database based on last write when is just going to be like, did they add or did they remove? And then it's going to be unclear. One of these might arbitrarily win. Now you might be thinking to yourself, well, we can actually make this work with something like a CRDT. So for those of you who are less familiar there, CRDTs would basically be a special data structure that goes on each of these leader nodes. And the idea would be to use something like a set CRDT so that when we add permission for a given user and then we remove it on another leader, basically the gist of the CRDT is that they will eventually converge to a value that makes sense. So for a set CRDT, what we would actually do is, we would basically say, here's a tombstone for, the permission, and here is the add of the permission. And then when we merge those via anti-entropy, we can see that the add and the tombstone are both present. Presumably, there can only be a tombstone if there was first an add at some point, and then that would go ahead and converge to the fact that the user no longer has permissions. Frankly, though, I think this is all a bit overkill. The reason being that we probably don't update user permissions that much, and as a result, I would rather just do single leader replication. That way we don't have to worry about causality. We know that all writes are already going to be reflected on the single leader. And so for a table like this, I would basically just use MySQL. I think that if we really needed to scale out our write throughput a little bit more, what we could do is just go ahead and partition it a little bit more, and the number of partitions is going to increase our write throughput. Okay, so we've gone on that nice little tangent. Now let's actually start to talk about file uploading. So one thing that would be majorly useful for us here is if we take a given file, we go ahead and split it into a bunch of smaller chunks. Now, why would we do that? Well, there are actually a couple reasons. For starters, when we upload files to S3, or object storage, or wherever we're eventually going to be putting them, we can do this in parallel. We have multiple threads on our client device. One of them can, manage each chunk and the upload of it. That should make things a little bit faster. Another thing is that we can only load the modified chunks on every single change. So let's say our client device already has access to these 3 chunks right here, and then this guy is new. We can just go ahead and pull this guy, right? So we have a lot less to pull from S3. We just pull 1/4 of the chunks. The con is, of course, that as a result of switching a bunch of files over to effectively a bunch of mini files, for starters, now our client has to perform a bunch of extra logic to figure out, what chunks actually changed on a given file edit. And additionally, we now have to keep track of all those chunks in our application itself. We need to keep track of them in the database. So let's talk about how we can actually do that. What we're effectively going to do is create a chunks database. And so what I have over here is an example of a file. And as you can see, we've got 4 different chunks for it. Now the chunks themselves are of course mini files, but within them, I'm also going to take the hash of each so that we can represent them nicely within a database. So what would that look like? Well, we've got our chunks table here with the following schema. We have an ID, a version, because keep in mind we have to keep versions of all of our files so that we can reconstruct older versions of them, the hash of the chunk, and then the link within S3 or maybe our object storage. So keep in mind that every single chunk for a given version is going to have its corresponding entry in this table, but at the same time, there are probably going to be a lot of duplicate chunks from version to version, and what that means is that we're going to be able to store less data in S3. We can use chunks multiple times, even if it's for different versions, which is good. Now, notice I said over here you could also use a wide column or a document format. There's no reason that all of these things have to be a separate row. We could just have one row per ID plus version. And then, the hashes would be like a list or something, or a map from hash to link. Anything like that would work. But the reason that I've basically created a schema like this is that if we index by our ID and then do an inner sort on version, it means that queries to the chunks table quickly allow us to figure out basically all of the chunk hashes that comprise a version. Because this is all going to go to one single partition, we don't need to do any sort of aggregation on an aggregator node, and additionally the index within every single partition is going to make those queries fast. So I think it's a pretty reasonable schema here. So let's actually start to think about what database we want to use for our chunks database, because I would think that as opposed to the permissions table, it's possible that at least for some documents, the performance of our chunks database might be a little bit of a constraint. Well, within a single leader, we basically need to be able to make sure that there is only one version of a given file, right? I can't have two users writing version 4 of the same file at the same time. So we would need to do some sort of locking, where basically if this guy says, I'm grabbing version 4, and another guy does the same exact thing, and we can do this either via predicate locks or just grabbing a lock on the file ID itself. We need the database to only say OK for one of these guys, and then for the other guy, basically go tell him to kick rocks and try again. And then this guy could, pull the file from the database, merge it in locally, and then go ahead and make a new version of it. That would be a lot more ideal. That being said, this works when there is a single leader. In the multi-leader case, it gets a little bit more complicated. So imagine that, we've got leader 1 on our left, leader 2 on our right. They both try to lock and grab version 4 of a specific file, but then on anti-entropy, what's going to happen is that these two are going to sync up with one another, both leaders, and then it's basically going to be arbitrary which version 4 is actually going to win, because tables like these typically tend to use last write wins. So one of them is going to get clobbered based on some arbitrary BS distributed timestamp, which doesn't really accurately reflect literal time. And as a result of that, now all of a sudden that whole file history that we wanted to preserve is not properly preserved because one of these guys just gets completely lost from our database. And that is the worst possible scenario. So if we did really need the extra write throughput of using a leaderless replication database, we could actually still do this. So I'm going to show how we might do that in a second by making use of something called siblings. Now, I've spoken about siblings a little bit in my systems design concepts videos, but the idea basically is that you have two writes to different leaders of the database, right? So same partition, but it could be two different leaders. And if we're able to detect the fact that they are concurrent, what we can do is actually store both of those writes at the same time, and then a future user who's going to load that file will be able to load them locally, merge them, and then upload just one singular version for the next iteration. So I'll explain that a little bit more concretely. So right now, imagine that this database for this file on the left here has a version vector 2, 1. What that basically means is that two writes have come from leader 1 to establish a new version, and one write has come from leader 2. Now, as you can see, clearly for this particular key or for this particular file, we're nicely in sync with leader 2, which also agrees that there have been two writes to leader 1 and one write to leader 2. So right now we're starting out as if everything is in sync. So the next thing would be, imagine that we've got two users writing to both leaders at the same time. So if this guy is going to write to leader 1, the version vector that he would procure would basically be 3, 1, because now there's going to be an extra write to leader 1. The guy on the right is going to be writing to leader 2, so he would have a version vector of, sorry, typo here, it would be not 2, 1, but 2, 2, because he's adding 1 extra write to leader number 2. And so eventually, when these guys do anti-entropy, which basically means that the multiple leaders are going to try and sync up with one another, well, what we would notice is that version vectors for 3, 1 and 2, 2 indicate that the writes did not know about one another, meaning they were concurrent. The reason they didn't know about one another is because when you look at these version vectors, you can see that at every single index of the corresponding version vectors, one is greater than the other and one is less than the other. And that kind of is going to indicate concurrency. Because concurrency, like I mentioned, means that the two writes were not fully aware of one another before they actually happened. And so again, if the version vectors are in this state, it means that they were concurrent. So what we can do is we see, hey, these two version vectors for these particular writes were concurrent. As opposed to just storing the files as v4, we can actually store them as v4.1, meaning this guy came from leader 1, and v4.2, meaning this guy came from leader 2. And so again, next time that a user goes and loads that file, they're going to have to merge it locally. Now, I think this does add a little bit of extra complication to our system that, frankly, we don't necessarily need. Again, I would prefer to just use a MySQL-based approach so that we can avoid storing siblings where we're doing locking, we're telling users that submit a bad request to basically go back, load the file again, and then upload it. But I can see the case being made for siblings as well if you just want users to be able to get their file up the first time that they try. So again, let's try and avoid storing siblings. If we really needed the extra write throughput such that multi-leader replication was necessary, then maybe we would have to do something like this. So again, write throughput as required. Now the last option in theory would be to use some sort of file CRDT, right? Where if it's possible that rather than ever having a client have to merge two files, we could somehow do it during the anti-entropy process, like use some special data structure here and here that somehow knows how to merge two different concurrent changes to files. But the issue with that is this isn't like Google Docs where we're exclusively working with documents. We could be working with documents, photos, audio, anything like that. And there's not really like a generalized CRDT to be able to merge any single type of file. So this approach probably isn't going to work. We're just going to have to ask our clients to merge them somehow whenever there's a conflict. So keep in mind that basically what I've said about these chunks DB so far is that we definitely want atomicity, right? Because we're uploading multiple rows at a time in our schema over here. You know, if I'm uploading 4 rows at a time, I want them to all go through or I want them to all fail. And we definitely need serializability because we want to make sure that if I'm writing to our single leader and then someone else is also writing to the single leader, that it's important that the database is going to explicitly choose one of us to grab that next version. So we need serializability, we need acidity, it would be nice to just have transactions. And so ultimately, I think that MySQL is again the best choice here. I do mention that partitioning is going to allow us to increase our write throughput, and we can partition basically to our heart's content as long as we ensure that all of the same file IDs are in the same node. We can just partition by hash range of file ID. And if even that really got bad, we could do file ID and version for partitioning, but I think file ID should probably be sufficient. Okay, so let's go ahead and talk about uploading the actual file now that we've spoken about uploading the file metadata. So again, the idea here is that the reason we break these files into chunks is so that not only do we get the parallelism here, but we can only upload the new chunks to S3, and that's going to save us both time and storage. So the question is, if we have to upload to both S3 over here and then also to the database, how should we do it? Well, we could use something like a two-phase commit, right, and ensure that everything that goes to S3 is also going to make its way to the database in terms of the metadata. However, the issue with that is it's going to seriously slow down our latency by quite a bit. And ideally, we want to be able to make this process relatively seamless from the client side. So what I've opted to do instead is let's imagine that these two chunks down here are new. Well, we should have 2 parallel writes at the same time, first to S3, and when we get news that those have completed, then we can upload our metadata to the chunks database. So as you can see, that's going to be a lot better on the client side, but it does come at the risk of certain files basically ending up in S3. And you know, if this write fails to the chunks DB, for a variety of reasons. Maybe it was a write that causes a merge conflict or something like that. Then now we're just going to have some ghost chunks in S3. So what could we actually do? Well, we could have a cleanup job, which occasionally pulls S3 and then checks if the chunk is somewhere in the chunks database to see if we actually need it for any of our file versions. Now you might be thinking, well, how can we quickly query the database once we know an S3 file name? Perhaps we could give every single S3 chunk name like, formatted like file ID, version, chunk hash, .s3.com or something like that. If we were able to do that, that would make life pretty easy, and then we would be in good shape. Okay, so let's go ahead and talk about file changes to users. So to make this clear, every single time a user is going to change a file, we would like to be able to show all the other users, user 1, user 2, user 3. We'd like to be able to show them that change as quickly as possible, assuming that their client is actively open and connecting to our servers. So this is where we start actually getting into a very similar design that we had for the newsfeed. Again, ideally, we don't want to be like polling for changes from our devices, because the idea is to have them there instantly as they happen. And additionally, it's very important to us that for a given client device, we keep the number of connections maintained to a minimum. Now, ideally, we would keep that number of connections maintained to 1. This is just going to use less battery on the client device, use less data. Generally, it's a good thing. And so the way we would do that is by having some sort of cache, similar to Twitter or Q or anything like that, that is representative of each user. However, there's going to be an issue here, which is that a certain amount of our files are going to be very popular, right? So let's imagine this guy has 10,000 users. That would involve publishing to 10,000 different places, and that is probably infeasible. We saw the same exact issue when we were doing the Twitter systems design. And so as a result, similarly to Twitter, what we can actually end up doing is opting for a hybrid approach. So the majority of the documents or the files in our system are going to have very few users that care about them. And as a result, when we see the changes to that file, we can push it to all of the given users that we need to. That's going to keep things nice and easy. However, for super popular documents or super popular files, many different users are going to have access. So it would be better instead if we could just push those files to one place, and then all of the users could connect to that. So yeah, maybe a user isn't going to have 100 open connections, one for each document, but they might have, say, 10 open connections, where we've got one for all of their documents that are unpopular, and maybe another 9 for all of the popular documents. Ideally, we would only have to have a few different places that you would connect to for the popular documents, because there are far fewer of them. So again, the idea here is that it's a little bit worse than having one connection, but it is far more pragmatic, because otherwise we would run into this problem right here, where we would publish popular files to 1 million different places. So let's actually talk about file routing, because we can draw out this approach and ensure that everything is going to the right place based on how many users have permissions to access it. So when a file gets changed, we need to go ahead and propagate the changes to the right place. And this is going to look very, very similar to the newsfeed design. So if you saw that, again, same kind of concept. So we've got our file right here. We're going to make an edit. First place it goes to is the chunks DB. Of course, S3 as well, but that's not too relevant for this part of the diagram. And so once we go ahead and make that change into our chunks database, what we can do is use something like change data capture. Can't speak this morning, too early. And so once we actually have all of those changes in Kafka flowing through, we can keep everything sharded by file ID, because at the end of the day, this is all a per file process. We don't really have to have data for more than one file at the same place. And this can go into an instance of Apache Flink, which can also be sharded by file ID. The reason we want to do this is so that for every single given file, we can actually quickly figure out which users have permissions for it. So the only way that we're able to do that is by also having the permissions DB use change data capture, which again flows into Flink. Now the interesting thing that you might remember is that we did say our permissions database would be sharded by user ID, whereas in this case, we want everything sharded by file ID. So our Kafka queue that is carrying the change data capture needs to also be sharded by file ID, so that basically when the permissions database gets changed, it'll flow those changes properly through. And then, of course, we can organize things such that we have good data locality. The reason we want to be using Flink here is that if we weren't using Flink and this was just some normal bum consumer, it would have to make calls to the database every single time to figure out which users have permission for a given file, and that would be very slow. And in addition, our schema isn't even good for that particular use case, so we would have to derive like a second database that is sharded by file ID instead. So that would be annoying too. I think this is a better approach. And then of course, once we see a given file, we can say, well, does it have over 100,000 users that follow it? If so, send it to one of the popular files, caches or queues or whatever we're going to eventually choose for that, which is going to be sharded by file ID. And then if it's not, if say there are only 3 users who are kind of caring about those changes, we can send it to the unpopular files area, and that would be sharded by user ID. So if there were 3 users, we would probably send that to 3 different places, depending on how our sharding works here. So hopefully that makes sense and looks very similar to Twitter. As you can see, learning one design is already coming in handy for getting better at the others. Cool. So let's talk about the actual metadata reading, because this is how a user is going to read a file once they see that the metadata has changed. So basically the question is, well, what device should we actually use as the sink, right? We say popular files, and I have kind of just like a general rectangle over here, but what actual technology should this thing be? Ultimately, I wanted to use Kafka, the reason being that users are basically just long polling from it, which may not be the best technological choice for our use case, but at the end of the day, I think it should be fine. Kafka is kind of built to be consumed from multiple times, which I think helps when you have multiple different users per a Kafka queue. And additionally, if a user were to go down for a few seconds, then come back up, rather than making a full big query to the database, they could just read from where they already were in the Kafka queue. So again, this is going to ensure that clients that go down can reread their missed changes. But anyway, the general process should look something like this. If this is our Kafka queue over here, and it's telling us for a given file what chunks have changed, you can see now that it's going to say, for example, file 2, the new version, has chunks C, D, and E. Now the client might say to itself, oh, wait a second, I already have A, B, and C locally. So you would see that there's overlap in file chunk number C, or letter C. And so then we can take the diff of those 2 sets and say, I'm going to S3 now, please get me chunks D and E. And once they do, you can recreate that file locally. So that should be a relatively easy process, which is good. Again, the fact that we're using chunks is going to allow us to actually load less of them from S3, because we just take what we already have locally and then get the difference. Okay, finally, we have made it to the end. So let's go ahead and get through this. As you can see, we've got the full-on design. So the idea over here is that we're going to start with a file writer on the left, and then a file reader on the right. So what can the file writer do? Well, basically, the first thing that they can do is add permissions for a given user. So that would go to our horizontally scaled permission service. And as we've already discussed, a permissions database, which we can shard on user ID and also index on user ID. So the query to figure out all of the documents that a given user has access to is nice and quick. Additionally, they can also upload a file. And when they do, we mentioned that the first thing that would happen is it would go over to S3. And then the second thing that would happen is we would go over to the chunk service. Now note that for our S3, we should most certainly be using CDNs to keep particular file loads fast for a lot of users. Specifically, our popular files, we definitely want to be loading those in the CDN. We could either pre-populate that from Flink, which is one option over here, or just do some sort of poll-based approach where as users are accessing chunks of files and those get particularly popular, the CDNs will just hold on to them, and that would be good for popular files as well. We would use like an LRU replacement or something like that. So again, the idea here is that first we put the actual chunk data, then we've got our chunk metadata going to our chunk service, which again is going to flow into our chunks MySQL database. We want to partition this on file ID so that loading all of the chunks for a particular file and version is particularly fast, and then index upon file ID and version within that, so that for a given version, we can quickly figure out what chunks that is going to contain. So from both of these tables, we're now using change data capture. Oops, accidental erase. From both of these tables, we are using change data capture to get data into Kafka. which is again going to be partitioned on file ID. And then we are going to get it into Flink, again partitioned on file ID. So if you recall, what that's basically saying is, hey, file number 1 has user 2 and user 3. And the reason we need to know for a given file which users have permission to it is so that we can either send that change up here over to the popular file changes queues. So that's option 1 if, say, it has more than 10,000 followers or 10,000 users assigned to it. Or option 2 would be, say it's only got a couple of users that need to know about these changes, send it to the specific partitions of queues that we care about for those users. So for example, if user 2 and user 3 were on different Kafka queues, maybe this would be a ×2, and we would have to send it to a couple of different places. The last aspect of this is we've got our file reader right here. So let's say this is user 2. User 2 knows what documents it cares about or what files it cares about, so it can go connect to the queue for user 2 automatically, and then it can connect to all of the queues for our popular files and kind of just filter out those changes as needed. Now, if there are too many of these popular file changes queues, then we may have to do an optimization to basically support some sort of data structure which tells us which popular files a given user cares about, and then as a result of that only connect to the proper queues that we need. That's not too hard too. It would take a little bit of extra derived data and a little bit of logic with our zookeeper, but ultimately I think for now we can keep things simple and just have the user connect to every single popular file queue. I imagine there would probably only be like 10 at most. So hopefully this makes sense to you guys. I hope it was somewhat useful, and yeah, in the next couple of weeks we're going to crank out a few more of these. So as always, if you have any questions or constructive criticism, none of my designs are perfect. I'm kind of making these up on the fly because I feel that if I look at everyone else's YouTube videos, all of my designs are going to be the same as them, and I wouldn't really have any novelty to what it is that I'm making. I even watched my old Google Drive video before making this one, and I can say for a fact that I saw a few of the choices that I made there and I didn't like them, and so that's why I deviated from that old design a little bit to use more of a hybrid approach rather than just having these user queues over here. So guys, have a great weekend, and I will see you soon.